Then next point, that is harmonics and overtones. When a string or an air column is set into vibrations by some means, the waves are reflected from the ends and stationary waves can be formed. An important condition to form stationary waves depends on the boundary. So, that boundary condition that constrains the possible wavelength or frequencies of vibrations of the system. These are called natural frequencies of normal modes of oscillation. The minimum of these frequencies is termed the fundamental frequency or the first harmonic. The corresponding mode of oscillation is called fundamental mode or fundamental tone. The term overtone is used to represent higher frequencies. The first frequency higher than fundamental frequency is called first overtone. The next frequency higher is second overtone, and so on. The harmonic is used when frequency of particular overtone is an integral multiple of the fundamental frequency. In strings and air column, the frequencies of overtones are integral multiples of fundamental frequencies. Hence, they are termed as harmonics. But all harmonics may not be present in given sound. So, the overtones are only those multiples of fundamental frequency which are actually present in given sound. So, the harmonics may or may not present in sound so produced. So, to understand the concept of harmonics and overtones, let us study vibration of air column. Before that, we have to study end correction. So, what is end correction, that we will see now. When an air column vibrates either in pipe closed at one end or open at both ends, boundary conditions demand that there is always an antinode at open ends, since the particles of medium are comparatively free, and a node at the closed end, since there is hardly any freedom for the particle to move. So the antinode is not formed exactly at open end, but it is slightly beyond open end. As air moves free to vibrate, there is in comparison to the air inside the pipe. So also, as air particles in plane of open end of pipe are not free to move in all directions, reflection takes place at the plane at small distances outside the pipe. So the distance between open end of the pipe and position of antinode is called the end correction. Now, according to the Reynolds, the first approximation end correction at an end is given by E is equal to 0.3 times of diameter, where D is the inner diameter of the pipe. Thus, the length capital L of air column is different from the length L of the pipe. So, here now capital L is the length of air column and small l is the length of pipe. So, we can write for pipe closed at one end, corrected length of air column capital L is equal to length of air column in pipe plus end correction. So, E plus L. Similarly, for pipe open at both the ends. So that is the corrected length of air column L equal to length of air column in a pipe L plus end corrections at both ends. So L equal to 2 times of E. Why 2 times of E? Because open end has pipe open, both the ends has 2 end corrections, so that it will be 2 times of E. Now here we have to see two conditions: pipe open at both the ends and pipe open at one end, or we can shortly say pipe close at one end. So vibration of air column in a pipe close at one end. You can see this figure, pipe close at one end. So bottom, its end is closed. Now consider a long cylindrical tube closed at one end. It consists of an air column with rigid boundary at one end. When a vibrating tuning fork is held near the open end of closed pipe, sound waves are sent by the fork inside the tube. Longitudinal waves traveling along the pipe of finite length are reflected at the ends of as transverse waves are reflected at the fixed ends of string. The phase of reflected wave depends on whether the end of pipe is open or closed, or how wide or narrow the pipe is in comparison to the wavelength of longitudinal wave like a sound wave. So at the close end there is the least freedom for the motion of air particles. Thus there must be a node at close end. The particles little beyond at the open end are most free to vibrate. As a result, antinode must be formed little beyond the open end. The length L of pipe and length capital L of air column are shown separately in all figures. Okay, that figure 6.9 and 6.10. So you can see this figure also. The first mode of vibrations of air column closed at one end is shown in figure 6.9a. Now, setup for generating vibrations of air column in pipe closed at one end. The distance of the antinode from the open end of the pipe has been exaggerated. So, this is the simplest mode of vibration of air column closed at one end, known as the fundamental mode. So length of air column L is equal to lambda by 4. So lambda is equal to 4 times of L, where lambda is the wavelength of fundamental mode of vibration of air column. If n is the fundamental frequency, then V is equal to n lambda. N is equal to V upon lambda. So n is equal to V upon 4L, where capital L is nothing but L plus E. That already we have taken in equation 6.13. So we can write this V upon 4 into L plus E. This is the fundamental frequency, or also known as first harmonic. Now, it is the lowest frequency of vibration of air column in pipe closed at one end. The next mode of vibration of air column closed at end is shown in figure 6.9b. So here you can see this figure, this B figure. Air column is made to vibrate in such a way, okay, that it contains a node at close end, and antinode is at open end with one more node and antinode in between. So if n1 is the frequency and lambda 1 is the wavelength of wave in this mode of vibration in air column, then we have the length of air column L equal to 3 lambda 1 by 4. So why it is? Because this one complete loop is your lambda and this is 1/4, so it will be 3 lambda 1 by 4. So which you can see here also about vibration of that air column. Now we have to consider about velocity of sound in second mode. Okay, so if you see its velocity, okay, it will be V is equal to n lambda. Okay, that also you can consider here. Okay, see here V is equal to n lambda, so n is equal to V upon lambda. Okay, another one you can consider V is equal to n lambda 1, so n1 is equal to V upon lambda 1, and which is equal to 3V upon 4L, because lambda 1 is equal to 4L upon 3, so it will be 3V upon 4L, and capital L is equal to L plus E, so n1 is equal to 3n. So this is nothing but what? n1 is the first overtone and 3n is the third harmonic. So remember that overtones are always numbered sequentially. So first overtone, but harmonic is different. Okay, so it will be third harmonic. Now, next higher mode of vibration of air column closed at end is shown in figure 6.10c. That is, the same air column is made to vibrate in such a way that it contains a node at close end, an antinode at open end with its two more nodes, and antinode is between. So n2 is the frequency and lambda 2 is the wavelength of the wave in this mode of vibrations in air column. So length of air column L is equal to 5 lambda 2 by 4, and lambda 2 is equal to 4L upon 5. So what is capital L? L is equal to L plus E. So 4 into L plus E upon 5. So velocity is nothing but what? V is equal to N lambda. Again you can consider for case 3. So it will be V is equal to N2 lambda 2. So N2 is equal to V upon lambda 2, 5V upon 4L, so which is equal to 5V upon 4L plus E, which is N2 is equal to 5N, which is nothing but fifth harmonic, 5N fifth harmonic but second overtone. So continuing in a similar way, for fifth overtone we get NP as following. So NP is equal to 2P plus 1 into N, which is required equation. So for a pipe closed at one end, only odd harmonics are present, even harmonics are absent. So N1 is equal to 3N, N2 is equal to 5N, N3 is equal to 7N. So in this way, only odd harmonics are present and even harmonics are absent. Now next point, that is vibration of air column in pipe open at both the ends. So if you consider a pipe open at both the ends, okay, where all harmonics are present, for example, N1 is equal to 1N, N1 is equal to 2N, N2 is equal to 3N, N3 is equal to 4N, so all harmonics are present. So in this case, boundary conditions are such that antinode is present at each open end. When a source of sound like a tuning fork is held near one end of the pipe, it sends the waves inside the pipe. So you can see in this figure also. So even though both the ends of pipe are open, the air inside the pipe is still bound by the wall of the tube. So as a result, air inside the pipe is little denser than the air outside. So when the waves travel to the other open end, there is a partial reflection at the open end. The partially reflected waves superpose with incident waves. Under the suitable condition, stationary waves will be formed. There is a maximum freedom for the motion of air column at both the ends, as pipe is open at both the ends. So how we will see it? Suppose compression produced by a tuning fork travels through the air column. It gets reflected as a rarefaction at open ends. Now the rarefaction moves back and gets reflected as compression at the other end. So it suffers a second reflection at open end near the source and then interferes with the wave coming by it a path depend upon its difference, that is 2L. So different modes of vibration of air column in a pipe at open at both the ends are shown. So 6.10 A, B and C are shown in figure. So 6.A, which is nothing but 2 antinode, 1 node. For B, 3 antinode and 2 nodes are there. So how it will work, that we will see. The fundamental tone or mode of vibration of air column open at both the ends is shown in figure 6.10A. So see this first figure. Okay, so there are 2 antinodes in first figure. Okay, if you notice this first figure, there are 2 antinodes open end and 1 node between them. So length of air column capital L is equal to what? Lambda by 2. So lambda is equal to 2L. N is equal to V upon lambda. So N is equal to V upon 2L, where capital L is equal to L plus 2E. Now V is equal to 2NL. Okay, so if you want to see this equation, you can see this equation here. Length of air column, that is L is equal to lambda by 2, lambda is equal to 2L. So N is equal to V upon lambda, so V upon 2L. So L plus 2E, that is end correction. Why 2E? Again it has 2 open ends, so that 2E. So V equal to 2NL. This is the fundamental frequency or first harmonic, or it is the lowest frequency. Sorry student. Next possible mode of vibration of air column at both ends, 6.10b, okay, where 3 antinode, you can see here 3 antinode and 2 nodes are there. So length of air column L equal to lambda 1, since equation 6.24, lambda 1 is equal to capital L, which is L plus 2E. N1 and lambda 1 are frequency and wavelength of this mode of vibration of air column respectively. So V is equal to N1 lambda 1. So N1 is equal to V upon lambda 1, which is equal to V upon L. So V upon L plus 2E. So N1 is equal to 2N. So this is the frequency of second harmonic or first overtone. So N1 is first overtone and 2N is the second harmonic. So in the next vibration of air column, open at both the ends, 4 antinodes and 3 nodes are found. So if you see in this figure, this figure, 4 antinodes are there and 3 nodes are there. So length of air column, capital L is equal to 3 lambda 2 upon 2. So lambda 2 is equal to 2L by 3. So 2 by 3 into L is capital L is equal to L plus 2E. So if N2 and lambda 2 are frequency and wavelength of this mode of vibration of air column respectively, then V equal to N2 lambda 2. So N2 is equal to V upon lambda 2, which is 3V upon 2L, because lambda 2 is equal to 2L by 3, which is equal to 3V upon 2 into L plus 2E. So N2 is equal to 3N. This is the frequency of third harmonic or second overtone. So if you notice this, N1 is equal to 2N, N2 is equal to 3N, that is frequency of third harmonic, second overtone. So all harmonics are present as overtone in the mode of vibration of air column open at both the ends. So continuing in this manner, the frequency of NP for pth overtone is what? Is nothing but NP is equal to P into N, P plus 1 into N, where N is a fundamental frequency and P equal to 0, 1, 2, 3. So it may be noted that sound produced by an open pipe contains all harmonics. Its quality is richer than the produced by closed pipe. And fundamental frequency of vibrations of air column in pipe open is double, and the fundamental frequency of vibration in pipe closed is same length. So using the formula and knowing the values of N, L and N correction, velocity of sound in air at room temperature can be calculated, and that is antinodes are formed little beyond the open ends of pipe. It is however not possible to locate the positions of antinode precisely. Therefore, in experiment, length of pipe is measured and N correction is incorporated. So practical determination of N connections are that an exact method to determine the N correction is what? Using two pipes same diameter but different lengths L1 L2, that is for pipe open at both the ends, V equal to 2N1 L1 and which is equal to 2N2 L2. So N1 L1 is equal to N2 L2. So you can see this equation by using this mathematical operations. E is equal to N2 L2 minus N1 L1 upon 2 into N1 minus N2. And for pipe open, a pipe closed at one end, that is V equal to 4 N1 L1 is equal to 4 N2 L2, where 4 will get cancel out, which is equal to N1 L1 is equal to N2 L2. So N1 into L1 plus E and N2 equal to L2 plus E. So by using this mathematical operations, you can calculate this value, and which is equal to N1 N2 L2 minus N1 L1 upon 2 into N1 minus N2. So in this way you can see these are the end corrections. Fine. Okay. Thank you, students.